All right. Hide this thing. All right. So anyway, I got a bunch of emails on the homework. That was good, and I think I respond to most of them. Any questions on that or no? All right. Anyway, let's see. So I took that this plot, right, which shows that flat. So it's not showing any power one. Doesn't show any power two. And I digitized the blue one and the green one. So you can do that pretty fast. But anyway, those are the ones I did. Because there seemed to be like the limiting factors in these. Then I just drew some lines. So I did a log plot. This is the green one. Let me just get it here. So it looks like, I mean, that guy's annoying. Here. So it looks like there's a flat background, so maybe you could subtract it, just subtract that off. So in the E1, that kind of works. You ends up being 0.04. You subtract 0.04, this is a line of -1 slope. So there is a persistence in the E1 if you subtract off the whatever flat is, but it never shows anything like this would be a power 2, which would be Gaussian, and then the other one is 1.6 minus 1.67, which is for a self-avoiding walk. So a Gaussian walk can cross itself. If you make it not cross itself, you get a different dimension, so weaker slope. So those are the two options. So it's not anything like that. In fact, it never goes less than 1. So this is just so if it's like a knee like this, that's on a log plot, a knee bell-shaped curve. If you made it linear, it would be a bell-shaped curve. And then the standard deviation of that is a rate of gyration. That's called Gounod's law. Okay, so basically, when you see knee like that, it means that there's just a size that you're getting. So it goes like rod, and then it ends at some size, which is like, so basically that molecule just looks like a stick. It's not a chain molecule, it's just a stick, right? It doesn't have any Gaussian walk. It's not a polymer, it sticks, right? So that's not mentioned in the paper. You probably should mention that the things aren't Gaussian chains at all, right? Which means if they aren't Gaussian chains at all, that means all the analysis to get, so that's kind of a problem, right? That's probably why they didn't mention that. It means that that's a pretty big problem, actually. Like all the stuff that is in the homework is bogus then. Like this equation applies, 1 and 2 apply for Gaussian chains. If it's not a Gaussian chain, it's not going to display that kind of elasticity, so it shouldn't behave that way. Right. So like that it sticks, that's kind of a problem. I guess that's one thing to say. So if they had kind of analyzed the data, or so maybe they did this and then they just didn't show it. That's one option. That would be the normal option. Like you see something that would totally screw up the entire analysis you did in your framework. So you plot the original data, which doesn't show it. The original data, because there's this flat background, you can't see any of these features in it. So no one could pick out that there's that problem with whatever this thing is, the green PNI, whatever. Anyway, so I didn't do all of them, but basically I did the blue one, which is the steepest one. And then you can't do that same thing. Like the more you subtract, it doesn't get better. Like this is just a smaller amount subtracted. If you subtract the 0.04, it's the same thing. It's just a little bit lower. I thought backing off it might show up. Anyway, this one does show like a persistence regime. So it's like a little bit -1. And the problem is usually if you talk about a scaling regime, you usually want 1 decade of scaling. Like that would be a normal judgment that you would make. Like, can I say that's a rod or not? Well, is it -1 over 1 decade of X? Then yeah, that would be definitely a rod, pretty much a rod. So this is like a quarter of a decade of X. So it's kind of wishy-washy. I mean, you are expecting it to be rod-like and is a signature of rod, so you kind of say that's okay. But then you go to the where it should go to a steeper slope after that, and it doesn't, it tails over. So it never reaches 2 or 5/3, these like a random Gaussian walk or a self-voting walk. It just kind of plops over. So you could say maybe that's polydispersity, or I don't know what you'd say. Basically, if that was polydispersity, you just say you had polydispersed sticks. Again, you don't have any Gaussian chain. Like there's no rubber elasticity to this at all. None, because it doesn't have Gaussian, so it can't have rubber elasticity. So it's kind of this little bit of a problem in this whole scheme of things. Um, I guess you could say um, that he's so these things are actually measured, not the network polymer that they make with it and then do the modulus test. So it's a different sample. Like they take these samples and they put them in solvents. It says what they do. So they take 2 milligram per ml, 10 milligram per ml. So these are, if you calculated, so what they should do if they did this right is like get the step length or get the chain size, some chain size, and then take the mass over that volume of that chain. If you took the chain size cubed, then you get the overlap concentration. Then you find out you have to run this below the overlap concentration, which would be something like, for rigid polymers, it's going to be like 0.1 milligram per ml. Like it's really small, pretty small. Like normal dilute solution, you say like 1 mg per ml for just like polystyrene and toluene or something, right? 1 or 2. So there, 2 is kind of okay for normal polymer. Rigid polymers, you're looking at like 0.1, then they're using 10. So 10, when you get to 10, then you get this problem that the coils start to overlap and then you can't, things get muddled. Like it isn't going to be very clear what's going on. Like, so basically they should have run the whole stuff at more dilute, and then run it for a longer time on neutron to get the statistics. So it's an experimental error. And then there's also the problem that they aren't chains at all, which messes up the entire thing with the data that they show. Right, so actually this is a pretty significant problem in the paper, I guess. And then so as you go, like I showed before, what happens when you go up above the overlap. See, I'm on 45. I'm going to go back. I mean, I briefly showed this. I didn't actually discuss it, I don't think, but I showed it for fractal aggregates, but it's kind of the same thing. Is it? Oh, here. All right. So you see your this is -4 because there's solid. This is like dust, so it has solid primary particles. There's a steep slope here. It would be -1 for chain, then it would be 2 for coil. That would be the persistence length or Kuhn length. And then it would end, like where you see the coil size. So you'd see the 2 scaling regimes in the transition. That's what you need to get the Kuhn length. So as you get, so that's below the overlap concentration. That'd be below 0.1 mg per ml for these things, but they boost it up to 10. So they're kind of over here, right? So in that case, you can't see the chain anymore. All you see is like a continuous thing. Like in a fleece, you just see a solid chunk of stuff. So you know there's stuff there, but you don't know like what size the fibers are in the fleece because you can't see them because they're overlapped, right? So the more concentrated you make it, the more overlap they come. The screening length, which is the size of the holes in the fleece, moves to the right because this is 1 over size. So you get smaller and smaller sizes, and then it washes out the data, right? All the data gets washed out. So if they're at 10 mg per ml, like they're like in this situation, right? They're way over. You can't see the scaling. So anyway, it's kind of, it's for people, NIST is supposed to be the premier place. So the measurements were done at NIST, supposed to be the premier place for this kind of work, in the world, basically with Grenoble in France and NIST in the US. Right, so it's kind of disappointing, I guess, that first they presented it this way, etc. Right, everything about this thing is disappointing. So like these NIST people, I guess it's who's a NIST person in this? Zoom back down. Let me just go down. Anyway, so I thought that was worth kind of looking at a little bit, but it's like the last person on the list is Snyder. Chad Snyder screwed up, right? Basically, he's like something. See what he is. I don't know him. He's probably a good guy and all, but uh, oops. And this guy, this is him. He's a research chemist. Blah 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 blah. Palmer's deputy division chief. So he's an administrator or something, I guess. All right. So anyway, so whatever. I don't know him. It sounds like he's kind of in administration. He's not actually. He doesn't actually have a background in neutron scattering. He just works at NIST where they have one of the best neutron places, supposedly the most like calibrated, standardized neutron in the world. But so he's not even in like the reactor division or anything. And he's also an administrator, so it's kind of a funny guy to pick up on this. I guess he's friends of Colby because I don't know why. Somehow he's friends with somebody. Anyway, so that's that. Any questions on that? You could put that in your answer if you're still working on it. Otherwise, whatever, there's a range of things you could say, but basically that would be like a full kind of look into that if you wanted to say exactly what's going on with it. Anyway, that's that. It's neither here nor there. So I just wanted to go continue on with the notes, today. So let's see. So we're talking about persistence length. How to get rid of that guy. I'm gonna do it. Yeah. All right. So anyway, so in Florey's first book, he came up with the term short range interaction and long range interaction. Right. So it sounds like basically it's kind of a bad terminology to use because it sounds like, well, you'd say like short range is over a short distance. On Did I push this guy? Cam on projector. Cam. Oh, it thinks that it's sending cam to projector. That's PC. Something's kind of screwed up with this thing. Could be operator, but never tell. I think it's a time lag. No, because I pushed it a while ago and it didn't do it. Is this thing even plugged in? Never tell. Plugged in there. This is extra cables. That's pretty weird because there's no. Oh, this is someone left their Reno. Someone left this thing. That's right. So anyway, this guy's not working today. At least the computer's working. It's good. Anyway, so I got some markers. That's a little tiny thing. Nope. Oops. Okay. All right. So anyway, so you have the chain, right? And then you say like short range interactions and long range interactions. This is Paul Flory. And like, I think it was like in the 69 or something, sometime around there. This is a Flory 1 book that's on the called Polymer Chemistry. Is the name of the book. There's a Flory 2 is the statistical mechanics of like long chain molecules. And this book he won the Nobel Prize for. And this book is kind of the parent book of polymer science. It includes polymer physics and polymer chemistry. Anyway, so anyway, so you have the chain. He called it short range interaction, long range interaction. So you'd think that short range interaction would be like short distances, and long range interaction would be long distances, but they're all like short distances. So the distances would be like 5 to 10 angstrom and 5 to 10 angstrom. That has nothing to do with the distance, right? So what it has to do with is like if you go along the chain, and he realized that you would have these restrictions on the path of the chain. So he called those restrictions like local. You could call it local chain restrictions. Those are short range interactions. The long range interaction is this thing that if it walks for a very long time, it can't cross itself. Like that's called excluded volume. The long range interaction is excluded volume. And short range interaction of these chain conformational issues. Like it has, like carbon has a 109 degree restriction. It can't really go far from that, right? So that would be one of the things. And then if that bond rotates that way, it's got rotational restrictions. So in terms of long range interaction, he ends up with the prism. So polymer rotational isomeric state model. So prism, they call it. So basically that has to do with that. If you rotate the chain, so if you have a bond, two bonds like that, and then you rotate it around that way, because there's groups sticking off. So you can have, it'll have different energies with that rotation, right? So basically, you can do a Newman projection of that thing. So you're going down the chain like that, then each of these is going to be tetrahedral bonds. So it's kind of like it's going to be like a flagpole on a tripod, right? So each of these carbons is going to be a tetrahedral arrangement. So if you're coming down the polymer chain, and this is also the polymer chain, you have these two. If it's polyethylene, you have two hydrogens there sticking off, right? And then this angle is 109 degrees, 109.5. And then that thing can spin around this carbon-carbon bond. So the way to look at that is this Newman projection, and you look down it like that. You look down it like that, and you see the tripod thing sticking out like that. So that bond, and if you go to the next one, you make a circle and you have the other tripod. And you have the polymer chain. So you have the hydrogens for polyethylene like that. So if you spin around, so you're going to spin around that carbon-carbon bond, polymer over hydrogen, polymer over polymer, that's bad. Polymer over hydrogen is good. And then polymer over hydrogen is good. So and in between, you have kind of a 3 toggle switch. It's like a switch that has 3 spots where it's happy, and one of them it's more happy. 2 of them it's more happy, one of them it's really hard to turn. That's when you get polymer next to each other. So we plotted the energy of rotation of that thing as a peak. And that's the gauche position where the polymer are over each other, and you have 2 trans that are weaker. You have trans and gauche situation for the thing. And then if you stick something else on this, like if you put on an aromatic ring that's polystyrene, then you'll see that that shape will change. That's the rotation. And the isomers are going to be, you can have one here, one here, one here. You have 3 isomers. So it's a rotational isomer. Each of those states is a rotational isomer. So there's also the KT of the room where the stuff is sitting. If the KT is up here, this stuff doesn't matter much because it's just flipping like crazy. It's like the springs on the switch are really weak at that point. But if you cool it down, then it gets to be a stiffer switch. So that means it's going to get stuck more. And anyway, so that you can think that the rigidity of the chain is going to be temperature dependent because it's going to be relating this energy barriers for the rotation to that KT, the room temperature. So that's kind of, so if you want to, so anyway, that's what Flory did in his second book, is calculate that for every polymer that existed in 1969. So basically every polymer, every commercial polymer, you know, so, and he was able to predict the entire structure of the chains from that. Like when you do a diffraction pattern of a chain in the melt, he could predict that. So, and he could predict the Kuhn length. What else could he predict? Kind of the density. He could probably get from that. He didn't get it because packing length didn't exist then, as V naught didn't exist. So, but he could have gotten that too. He could get everything because he could get the actual chain structure from it, you know, just from a mathematical calculation, not a simulation. Anyway, so that's kind of the idea of this RISM thing. You don't see it mentioned at all in the literature now. Like no one does RISM anymore. So it's a little bit of a dead science in a sense. But it's kind of a basis for, anyway, for the first step of looking at things, it's a basis of the nomenclature and things. For instance, like short range interaction, long range interaction come from this. You know, so the first thing you looked at was short range interactions, right? So this RISM doesn't have anything to do with long range interaction. It's just the local bonds. So it's just going to decide what the Kuhn length is basically, and then how the things pack together, right, on a local scale. Anyway, so as that said, so the simplest thing you can do is say just forget about all the details of the chain. This is from Doy's little book. Okay, so you say you're going to just have a Cartesian coordinate system, whatever. So you have like X, Y, Z, right? And then you can see it. So you call it the coordination number is this capital Z is 6. You have 6 ways you can go on a Cartesian. Right. So, and then you're going to do a random walk on a Cartesian. So you're going to talk about these Ri steps, and then Ri plus 1. It's like the next step. So there. So if it's a random walk, Ri plus 1 could go that way. It could go back the same way that it came. If you walked in, it could walk out because it can walk on itself. That would be a random walk. For that, you know, like R squared equals the number in the thing, and then I'll just call it L squared. Like there's an absolute value of R is, I'm just calling it L here. Right. So that's the thing that we got, because if I doesn't equal J, that averages to 0. And if I equals I, cosine of 0 is 1. So it's just going to be 1 times and then sum over all the i's. So then that will be n, this n i's. This goes to n. And you get n, and then it would be L squared. Right. So that's the random walk. All right, so, but in the case, if you wanted to exclude that, that would be like the simplest kind of short range interaction. You don't go backwards. Right. So then at that case, anyway, I have this written up in here, but so if you do that, you would have, so this thing would equal 0. And then if you do that, no short range interaction, okay, just for the next step, like, so the average next step would be 0. The average would be 0. But if you wanted to say like it excluded the previous one, it would be this number that you don't know what it is. And that'd be Z minus 1 of those. So coordination number minus 1 is 6 minus 1, there'd be 5 of those. Then there's the step that's missing, right? That goes backwards. That's the backward step, so it's minus Ri. Right. So then you could say, well, if you can say that, that's an equation with only one unknown to it, so you can solve for that and you find out it's this thing. So that means that your step no longer, average next step isn't going to be 0. Your average next step is going to be the step that you missed divided by 5. Z minus 1. So Z could be a big number if it's not in a Cartesian coordinate system. but 6 is kind of a convenient one to use because it's a number. If it's completely free, it's hard to say what that number is, right? So anyway, 6 is kind of a nice number. Anyway, so this is all just hypothetical, right? So saying like, well, what would happen to this NL squared thing if you do this? So it's just like, but this is the same kind of thing you would do if you put bond restrictions in. If you conjugate the chain, if you make it tactic, meaning that if you have polystyrene, so tactic means that if you're going down the Newman projection, right, you have polymer, and then the polymer, so I'm going that way. Well, I have like A and B, I can put my aromatic ring here or there. Right, so if I go left, and then I continue down the chain, and the next time I get that choice, I go left. That's called isotactic. It's kind of a 3D arrangement. It doesn't mean that you have like this, because these things are free to spin around, right? So you couldn't tell to look at it. If you took a picture of it, you couldn't tell because they can spin freely around. But there's a difference in left and right in it. So if it goes LR, it's let's see, LLL is isotactic, LRL is symbio, and LRR is hetero. There's 3 kinds of these are dyads, and these 3 are triads. So one of these is a dyad tacticity, and 3 of them is a triad tacticity. So that tacticity will change at Kuhn length. But more it's regular the tacticity, you get a longer Kuhn length. Just because of that, there's an added feature that when it has tacticity in the chain, like an isotactic polypropylene, which is a normal kind of polypropylene, just like this one, where the side group is a methyl group, not a it's a CH3, not an aromatic. That forms a helix, right? So the tacticity stiffens it up because the things are kind of interfering with each other. And then because it's tactic, it'll form a helix, and a helix has a huge effect. If it forms a helix, then that's going to be rigid. Like the helix is a rod, right? So a lot of polymers would form a rod if they're in a tactic form. It's an addition of the tacticity and the helicity, right? So these things, I mean, Florey didn't exactly consider these things, I don't think. I think it's inferred that it comes out when you do the isomeric state model, the helicity comes out of it too, like it falls out, right? So all those things can just be piled into, it doesn't go backwards, like in Doy's thing, right? So it's pretty simple. So you have just this thing, like this is just the thing. So then you say, well, I want to do this double sum, and then I'm going to say like the other guy is going to be this thing, and it's going to be how many steps down is just going to be, this is a probability, so I just multiply it. So if it's 2 steps down or 3 steps down, it's going to be that probability to the 3rd power if it's 3. Right? So I can just say R dot R is just going to be like this expression. How many steps are between the 2? So I can plug that guy right into this thing. I can just do that sum, which can be solved analytically, which is nice simple thing, kind of simple. So you solve it. It's like a sum of powers geometric progression rule. So you can use a geometric progression rule because if you say it goes to infinity, so it's an infinite chain, use a geometric progression rule, you can mess around with it, and then you can just get that answer. I mean, you can do that. I mean, it's a little messy to do it, but basically just use geometric progression in this expression, substitute for A and R here, and you get that answer, which is a simple analytic answer. No simulation, just the answer. Right? So what you can say about that is that it's still Gaussian. Like you still have the end-to-end distance still goes with n, not with end-to-end distance squared still goes with n, not n squared. So it's not ballistic. It would be n squared if it was ballistic. It's Gaussian because it's n. And then this b squared, and then you have this weird term. It's analytic. So I think it's 6/4, which is like, I think it's 1.67. Right. So you could say like, well, if I just kept n the same, then what would what would B be? So you just have so this is a larger number, it's bigger than one. So you made the step larger by putting in this can't go backwards. So you've increased the Kuhn step of it, right? So anything you do, you can't actually decrease the Kuhn step from the bond length because that's kind of fixed. That's a rod, it's kind of a rod, I guess. A carbon-carbon bond is kind of a rod, so you can't get smaller than that, but you can get larger. So you can only get larger. It's the only option that gets larger, right? So if you want to, anyway, so if you did that, you didn't get that this B was 1.2 times the original B, which is a small effect, right? But actually, N changes too, right? If you have longer, so you have the same chain, you have a longer steps, you have to have less steps to it if you use the longer step. The two things are linked, right? But luckily, so you have two unknowns really, N and B. If you ignore that, just say B is 1.2, the other B. But because there's two unknowns, that's not exactly the right thing to do. So basically, there's another number. You know that if you take the chain, it's the same chain. So if you fully stretch it out, there's a length, the contour length of the chain. Or contour infers that you have the squiggly path and you're just going to follow along the contour of the path. So the word contour length comes from because you have the squiggly path and I'm going to like walk along that path. So I'm following the contour of it. A 1D contour. I mean, normally contour is like a landscape, right? Basically, there's a 1D contour. Or you could take the chain and fully stretch it out. And if you walked on that, you'd walk the same distance, right? So that distance is NL. That's your capital L, the contour length. Right. So NL equals your new short range interaction and times your L short range interaction. And then so that's equation one, and equation two is you have NL squared is your new short range interaction L, your new short range interaction guy that, and then Z over Z minus 2. All right, this 1.67, I think. It's kind of weird. Anyway, so I see so you have two equations, two unknowns, you can solve it. Right. So if you solve that, then you get, instead of 1.2, it's actually a little bit bigger, 1.5. So you've increased by a half the step length just by not going backwards. Just kind of significant, I guess. And then you've reduced the number of steps. So you can solve both. You can reduce the number of steps by kind of 2/3 of the original number of steps. But the big impact is if you figure out what the density of the chain is. So you just didn't step backwards. What's the density? In other words, the mass of the chain divided by the volume. So that R squared to the 3/2 would be the volume. R squared to the, 3/2 will give you the volume, right? So you do that, figure out the volume, take the ratio, you find out that it's 1/3 of the volume. So it's a big effect on the volume. So what does that mean? That means that, so 1 over this density is the overlap concentration. That's the concentration that you have to shoot for when you're trying to get a dilute solution to do the neutron scattering measurement. Right? So it's 1/3. So if you were playing around with 2 or 1 mg per ml, you're talking about 1/3 of a mg per ml. That's a big difference, right? So it's like you have to kind of consider, and this is a small amount of rigidity. Like you've only increased it by 1.5 the bond length. These kind of conjugation things are going to be like 6-10 times the bond length, right? All right. So this 6. You go X plus X minus, Y plus Y minus, and then Z plus Z minus is 6. So that's from crystallography, that's a common number to use. If you've never done crystallography, it'll seem like weird. Basically, if you do crystallography, you always have this 6 for a cubic system. 6, coordination number 6, simple cubic, right? So anyway, so Z is the coordination number. You can run into that if you run into that a lot. Like there'll be like, oh, if you make just a dust bunny and you have particles, like what is or any kind of simulation, you're going to have coordination, like how many interactions is it going to have in space for each thing, each sphere that you have floating around. Coordination number comes up a lot, not just in this, so it's kind of like a common number to use. Anyway, so the Doi thing's it's good to read that little Doi book. It's on the webpage somewhere. If you just look Doi, it's a very short book. It's a paperback. actually it's written pretty well. It's all equations, but they're all like really simple. He takes you right through everything very simply, so it is like math, it's not like like the Russian book is also simple and it's more wordy. So if you really are math averse, it might not be the best one. But I think for me, it's like a pretty good. All right, so this is kind of interesting to look at. Tells you quite a bit just from one simple thing. So it gets more complicated. You could look at, all right, so Flory looked at these two, bond angle restriction, rotational restriction. Then you can talk about steric interactions. Flory did steric interactions too. So if you put a methyl group on the side for polypropylene or an aromatic group for polystyrene, well, those things interfere with each other differently, right? In other words, because one's bulkier than the other. So there's more of a steric interaction. Tecticity I mentioned, and then conjugation we looked at in the paper, the double bond, single bond, double bond thing that makes it planar, so it makes it rigid. And then main chain aromatics is kind of partly conjugation, partly steric. And then cyclics in the main chain make the chain stiffer. Then you kind of talk about biopolymers, right? Or water-soluble polymers that have charges on them. Those charges, so this thing is a little bit slightly complicated. So in that case, you have a chain, it's a polyelectrolyte. And you're going to have some kind of charge on the chain that's spaced at a distance like A. So there's going to be a charge spacing. And then you also have the Kuhn length. So the Kuhn length can be bigger than A, or the Kuhn length can be less than A. Right. So if the Kuhn length is bigger than A, then you see an impact. If the Kuhn length is less than A, you don't exactly see an impact of it. So you can't straighten it out. I think that's how it works. Anyway, the ratio of those two impacts, like whether it has an effect or not, right, on the Kuhn length. It'll affect the interactions between the chains, no matter what the spacing is. But basically, then there's another number, the Debye screening length. So there's three lengths. There's the Kuhn length, this charge spacing length, and then the Debye screening length has to do with if I have a plus charge and a plus charge here, there's this Q squared over R interaction potential between them. But if I put another charge here, that interferes with that and it screens out the other charge. So the higher the concentration, so this thing depends on 1 over the concentration squared of charges. Right. So basically, the higher the charge density on the chain, the shorter this lambda gets. And once lambda gets below A, then the charges can't feel each other, so they can't affect the chain. Yeah.
So what you're saying is short-range interactions will significantly affect the overall conformation of the polymer chain?
No, doesn't affect the conformation at all. Like, in other words, the conformation means Gaussian or self-avoiding walk. That's the conformation. Like, how does it accordion fold up? I mean, is it an accordion or is it like a rope or what is it? Like, how does it crumple? So it's still in L squared. So it isn't affected that. It's only affecting this local short range interaction thing. The conformation is affected by the long range interaction. Kind of, can it cross itself or not? Like after it wanders along and it forgets where it is on the path, and then it sees itself again, does it repel itself or does it just ignore itself? What's that interaction after a long travel down the chain? So yeah.
To know how the SRI affects the stability of polymer chain.
Yeah. Well, you mean that, all right, the stability, the polymer chain's there, it's fixed, right? It's not, unless you burn it. But the solubility, right? Like, in other words, if you put it into solution, is it a stable solution or not? So what causes a solution, like entropy? Like when you mix two things, it's driven by entropy, randomness. And this is something that makes it become less random. So it's not going to mix with things as well. So the big problem with processing, like you'd make, if you can straighten out the chains and make a fiber with it with fully straight chains, right? You can make a material that's the strongest material, like stronger than diamond. Right. So if you could take just covalent bonds and make straight chains, you make a super strong material. Right. But that stuff, once you make those super straight chains, you can't dissolve it. It's like Kevlar, they have to dissolve it in like I think concentrated sulfuric acid, and they have to spin the fibers at like 100 C or something really hot. So hot sulfuric acid kind of can dissolve Kevlar enough to spin a fiber from. Then you can make a bulletproof vest. They're still not perfectly straight chains. They still got some kinks in them, right? But they're straight enough that you get like a bullet can't pass through them. And then you can take, so that's true. Like if you start manipulating the short range interaction, the solubility goes to 0, like conductive polymers. So the same thing, if it's all conjugated, it conducts electricity. Great, I'll make a wire with it. Well, if it's this squiggly chain, it's conductive, yeah, but it's going nowhere. Like the electrons are going no place, right? So you have to have them in a straight line. In order to get that, you need to be able to process it like spin a fiber. And you can't get it into solutions, you can't spin a fiber, right? So it's this problem, like you can't, you got the goal on the one end, like on a small scale, you got exactly what you want, conductive fiber, super strong. And on the other end, like, oh, let's make it. And you find out, oh, I can't make it. So either you can make it or it's going to be of great properties. You can't have both, right? So you can get around that by not the conductivity issue, but the strength issue. If you take, and I think they must have discovered this by accident, but like DSM in the Netherlands developed this. But basically, you take polyethylene and you make it ultra high molecular weight, so 10 million molecular weight polyethylene, linear chain with no branches. And then, all right, that can't be processed. The only way to process things like that is to make it into a powder and then do rotational molding. So you can throw it into a big bin and just spin it around. It'll coat the thing. That's the only way to, because you can't make a fluid from it. But you can put it into a solution and make a gel. So a really thick gel. So they put it into a solution at like 1% into chlorinated benzene, which is, I mean, it's a solvent for polyethylene. And then you can make a gel and you can spin that gel and then you can get the polyethylene chains to be perfectly straight lines and you can make a bulletproof vest with polyethylene. Like the same thing a milk jug is, you can make this super strong fiber from, and you can spin it into vests. So like a lot of the, like I think the helmets, the army helmets are made from this kind of polyethylene. It's just polyethylene plastic, like wax, but basically because the covalent bond is so strong, right? So anyway, so there's a lot of nuances to it, but basically the solubility is a big issue, but yeah.
If the molecular weight is significantly higher, or if it's higher, then the specificity would be more difficult and vice versa.
Yeah. Yeah, the higher the molecular weight, the less soluble. Yeah, that's true. Yeah, I think that's in general. Yeah, if you want it to dissolve, you would get it, you'd make a lower and lower molecular weight. Yeah, the higher molecular weight one should have more conformational, but I think it just anyway, that's how it is. Yeah, actually, we'll look at that. We'll look at like miscibility, and we'll show like how the molecular weight dependence of it's got to do with how the well, we'll show how it works. There's a scaling dependence from molecular weight and solubility too. I don't think I can put it in words right now, but basically, yeah, the high molecular weight won't dissolve. That's the thing. So anyway, so the charges, and then yeah. Yeah, because they're rigid, they're conjugated chains. So they have a lot of the short range interaction is really high for conductive polymers for conjugated, because they're conjugated, because it's single, double, single. When you have conjugation, the whole thing has to be on a plane. It's got to be a planar structure. So that means the whole chain, if it's conjugated all the way down, is just a sheet, like a ribbon, kind of, So basically it would want to just be a straight ribbon all the way. It would have to be like totally straight. I mean, there's some, I guess it must bend some, but basically the idea is that like at least locally it's a sheet. You know, so basically that makes it have huge short range interaction. I mean, you don't even think about it like it's an interaction because it's just bonds, right? So, I mean, but so he called it short range interaction. So you can blame Flory for the nomenclature, and no one's going to change it now. So that's stuck with that. Anyway, so it's that business. So if you so anyway, so this C infinity, so the characteristic ratio is the way you kind of talk. I think Flory invented this. So you talk about C infinity, okay, infinite molecular weight. So if you take any measure of the chain, so there's number of the units in the chain, and it's always going to be NL squared. So number of Kuhn units, L Kuhn squared, or it could be the number of bond units, L squared. So you say, well, the Kuhn is the actual structure, and this is the actual size that you can measure with like neutron scattering, right? So you have the contour length times L Kuhn would give you the length of the chain then, right? If you say NL has to be contour length, and then the same thing goes for the bond, like L of the bond, NL of the bond, and then becomes capital L, and you have L bond, and you have C infinity is a number that modifies the chemical thing that you can look up in a handbook, and then the actual size of the chain. Like how big is a chain? Well, calculate the number of bonds, the chemical bond unit length, and then times the C infinity gives you what the actual length of the chain is. So it's a useful tool. And if you mess around with this, you find out that that thing is just the Kuhn length divided by the bond length. Like you just, the L's cancel and just get the ratio of those two lengths for this number. So this becomes like a number. So like polyethylene 7, 1.54 bonds gives you the Kuhn length, right? And then PEO is the hand sanitizer stuff. Polystyrene 10. So this is more rigid than that. So you can say rigidity. These are all, that one is actually a hetero main chain, but so like 6.7 and 10, you can compare, that's just the side groups. That's just the steric. Yeah. Yeah, the B, yeah, B and L. Sometimes it's called A, like they use different symbols for it. B is a bond length. I think B is a number that Doi uses in this little book. So people use different symbols. Basically, I don't know why. I mean, different groups of people, like theoreticians like to use B. I guess experimental people like to use L. I'm not sure why. It just kind of people get used to using a certain number. What's that? Yeah, the Kuhn length. No, the bond length is for polyethylene is 1.54 angstrom. And the Kuhn length for polyethylene is going to be 6.7 times that. It's going to be C infinity times the bond length gives the Kuhn length. So it's like 10. No, B is the same. Oh, yeah, and I'm just saying B effective is the same as the Kuhn length. I mean the squiggly, yeah.
Can you explain what it means by like characteristic ratio exactly?
Yeah, it's a number that tells you how stiff the chain is compared to the chemical bond. So it's relative to the chemical bond, how basically it's a ranking of how stiff the chain is. So if it's just a chain of random walk carbon bonds, the Kuhn length, this character ratio is 1. The bond length is the same as the Kuhn length. So that means that there's no 109 restriction, there's no rotational isomeric restriction, there's no steric interaction, there's no charges, and the carbon bonds can freely flop around like a chain mail, right? So because there's all this stuff, that has to be a bigger number, bigger than 1. Can't be less than 1, it has to be bigger than 1. Yeah.
So, in order to have any polymer conductive, they need to have a straight line or as straight as possible, or as linear as possible.
Right.
But what if the case is polymer have a tendency of clumping up? like long chain polymers like this,
Mhm.
but till the time they are attached to each other, electrons will form the shortest path possible to conduct and still having more flexibility.
You mean make it conjugated and non-conjugated and connect together?
That will still be conductive having flexibility.
Well, it'd have to jump over the squiggly part. The electrons would have to jump through the other part.
Till the time they are squiggly, but they are attached to each other, it will still be conductive path.
Yeah, people have messed around with this, like the way you're talking about. So there are people that make these things that have done these things kind of. You mean to increase the solubility, you attach like a flexible. You can also, all right, the way they've done it mostly is that you have the rigid chain that conducts and you put side groups on that are soluble. So it
Yes.
still goes along the route and then you have these soluble things on the side. But you can't do that without messing up with the conjugation, you know? That's what happens. So that it draws the electrons out and then doesn't do this resonance structure where the double and singles flip anymore because the electrons get trapped on whatever's up here. Anyway, there are solutions to it that have worked, you know, but in general, as you stick things onto it, you find out the more you try to mess around with it, the more you ruin the conductivity of it. The conjugation falls apart when you start doing things to it. So the best thing is polyacetylene, which is totally insoluble in anything. It's just like single, double, single, double, single bubble, and some hydrogens off the side. That's it. That's the best one, but basically you can't do anything with it. I mean, once you make it, it's there. However you made it, it's sitting on the. That's it. You know. So and then you like the anyway. There's a bunch of different conductive polymers that people have messed around with. You know, because it's also of interest for high strength fibers too. So like DuPont spent a lot like developing Kevlar and a whole slew of high strength fibers. You know. Because they're all condensation polymers, so they had expertise in that from Carruthers and things. So anyway, people have worked on it since probably conductive polymers were big, kind of the beginning part was probably the 1980s, 80s and 90s, something like that. So it's been around a really long time, like 50 years or something, you know. Not 50, but maybe, I mean, McDermott won, there was a Nobel Prize in conductive polymers, McDermott at UPenn and another guy. So this field has a Nobel Prize in it, you know, for developing conductive polymers. But so a lot of people, it isn't like, all the people that work with McDermott, he had grad students and postdocs, so they all got the top jobs, right? So they're everywhere. It's like people are doing this all over the place. But then that's already gone through its transition where I don't think there's that many people doing it now. You know, so I think that's kind of died to nothing. And then they've probably made as much. So a lot of these LED systems are focusing on this type thing. So it's all application oriented now, I think. But so anyway, it's interesting. Maybe I can find a paper on that this week, you know. That's really good. Like LED, polymer LED stuff, you know. The problem is it isn't really physicsy at this point. It's more like application, like, so what color can you get? And is it better response and things like that? But yeah, so it is a field and it's an industrial field now. Like the LED TVs, I think are like conductive polymers now. Because with the ceramics, you only get certain color ranges. And with this, you can tune it with the side groups. So you can get the full spectrum. So anyway, it's industrial, you know, at this point. So anyway, so yeah, why don't we, I think we're out of time, so why don't we quit there? Thanks. Oh.
Yeah, this one I have read.
But